Okay, I just wanted to go over some of the problems on our exam that gave us maybe a little more difficulty than others. This is a Calc 2 exam. First question here is we want to solve the initial value problem dy over dx equals 3x squared times y, and we have sort of initial value y of 0 equals 5. Okay, so most of this people understood fairly well here. The goal is to recognize this as a separable differential equation. So to solve this, you sort of separate the x's and y's. So you get a dy, you get a divide by y. So you divide by y on both sides, move the y to the left, and then you take the dx, move it to the right. You get 3x squared dx. Again, this was just fine here. Next step is we want to integrate both sides. So on the left, we integrate with respect to y. On the right, we integrate with respect to x. And then what we get here is, let's see, on the left we get natural log, really absolute value y. Integrate 3x squared, you get x cubed, and then you get a plus c. So again, people generally did just fine here. But now the goal is to solve for c, and that's where we're going to use this y of 0 equals 5 here. So what this means, y of 0 equals 5, that means when x is 0, we get y equals 5. So it's like y of x here. So you could plug those in right here. So let's just see what that would look like if that happened here. So if you plug those in now, what you'd get is natural log absolute value 5 equals x is 0 cubed plus c, and that gives you a c equals natural log of 5. And I'd be okay at this level, sort of, if that's what you did. And if you did that, your answer is really natural log absolute value y equals x cubed plus natural log 5. So I probably would have given you full credit for this. I don't think anyone did that here. What's more natural to do, instead of going this route and plugging in for the c now, is to sort of solve for y first. So that's generally more ideal in terms of being able to use this solution. So to solve for y, I'm going to do e to both sides. So e to the natural log absolute value y equals e to the x cubed plus c. And then e to the natural log absolute value y is just absolute value y. And then we do something a little bit funny here. This e to the x cubed plus c, there's a rule of exponents that says this is e to the x cubed times e to the c. Now if you think about things this way, you don't want to solve for c necessarily. You can just solve for e to the c. Since sort of if you solve for c, you could plug that in. So what's customary here is to create a new constant. So I'm going to write this e to the c out in front, but I'm going to call it, how about c2 e to the x cubed here. And often what's a little bit confusing until you get used to it is people sometimes just write c for c2, so they don't have to write a different subscript every time they change the constants. It's still just a constant I'm going to solve for. Okay, so we get to this form, and now we can really sort of get rid of the absolute value as well. So you'll get y equals, well, it's either going to be a positive or a negative version of c2 e to the x cubed. So you really could have sort of the positive y's or the negative y's. And really, if you look up here, our initial value has a positive y. So we're just going to do always the positive versions of y. So you really get a y equals c2 e to the x cubed, and we're going to have a positive c2. Okay. So now once we get here, we can plug in the x is 0, the y is 5. So we get a 5 equals c2 e to the 0 cubed is 0. E to the 0 is 1. So that tells us 5 equals c2. And what you get then is your final answer is y is 5 e to the x cubed. And that's sort of the ideal of what we were looking for. Note, that's really the same thing that we have up here. If you look at what would happen to this c, you have e to the c as this 5. Well, if I do e to the c instead of c2 is natural log 5, but that's just 5 our c2. So essentially what we're doing with putting this c2 here is you don't have to deal with the natural log and the e to that. It generally just makes things simpler. Okay, next question I want to talk about. This was number 5. We're trying to do an antiderivative of 16x cubed plus 5 times natural log x dx. So I'm going to go through what I saw a lot of and talk about sort of what's wrong with this. Sort of the right thought process, but there's one technical aspect that kind of makes it all fall apart here. Here, I think what people identified pretty well here was you had some 16x cubed plus 5 multiplied by natural log x. And a lot of times when I have a multiplication, I'm trying to find an antiderivative, I want to use integration by parts. Okay, and that's really what we're going to do. But what people would do here is I'd see a lot of this. U is 16x cubed plus 5. Oops, let me write that 5 a little more cleanly. And then dv here would be natural log x dx. And then you go, okay, I wanted u to be this because when I do a du, I differentiate. That's going to give me 48x squared dx. And then I want to find the v, and here's where the problem is what I saw a lot of is this, v equals 1 over x. But that's not correct here. So here we're going to do an antiderivative of natural log x, but it's not the antiderivative of natural log x that's 1 over x, it's the derivative. So if you did a derivative of natural log x, that would be 1 over x. But what we really wanted to do here was find an antiderivative of natural log x, which you can do with integration by parts, but it's a little trickier. So this here just sort of is wrong. And people would go through and evaluate that and get certain things, and your integration by parts formula, that would work out just fine. You'd get something, but it's sort of the wrong thing because of this one step here. Okay, so what were you supposed to do here? And you're supposed to still use integration by parts, but when you see a natural log x, what's typically a lot of times works out is you'll do a u is natural log x, and then the dv is the other thing. In this case, that's 16x cubed plus 5 dx. And the thought process here is, well, I don't know how to do a nice antiderivative of natural log x, or maybe I have to do some work to work that out, but I can do a derivative of natural log x. So I do a du. Derivative of natural log x is 1 over x dx. And now I'm going to integrate this sort of dv part to get v. That's going to give me higher sort of degree polynomials, but that's going to be okay here. It'll work out in the end, although it sort of should make you a little suspicious at first. So we integrate this and we get 4x to the 4th. Integrate 5, you get 5x. Whoops, I was going to parenthesis, but I don't actually need that. And now we can do our integration by parts formula. And that's u times v. So that's natural log x times 4x to the 4th plus 5x. That's a little ugly, but we're already done. We don't have to anti-differentiate it, so I don't even really care what u times v looks like. Minus the integral of v to u. So v is 4x to the 4th plus 5x. du is 1 over x dx. And so you can now distribute this 1 over x and turn this into a polynomial. It's going to reduce the degrees. So what we'll get here, let's see, you have your natural log x. I'm going to write that 4x to the 4th plus 5x in front. I like to do that just because I worry that I start thinking that the 4x to the 4th plus 5x is inside of the natural log. Minus an antiderivative, let's see, we get 4x cubed plus 5 dx. So we get is 4x to the 4th plus 5x, natural log x, and then we just do our antiderivatives. Let's see, 4x cubed is going to give us x to the 4th over 4. The 4ths will cancel. That's a minus x to the 4th. Integrate 5, and you get 5x. And I get the minus to carry through, or you do parentheses around the whole thing here. And I get a plus c. So that was our answer here, and I saw an awful lot of people doing this antiderivative of natural log x is 1 over x, which I kind of understand what you're thinking, but it just isn't the right thing. Next one. Okay, this one, cosine to the 5th x sine x. I think a large number of people got this correct, but doing it in a much less efficient way than is possible. So let me show you what people did here typically. Actually, I think this was more common, which probably means I messed something up explaining this or didn't emphasize the right things, I suppose. So what I saw is people saw this cosine to the 5th x and thought, oh, I'm going to split that up as cosine x times cosine to the 4th x times sine x dx. And so this 5 is odd, so I can pull that apart. And then what I'm going to do is I'm going to keep my cosine to the 4th x as cosine squared x squared times sine x, and I'm going to pull this cosine x over here, preparing for a substitution, and I want the cosine x with the dx, although I don't technically need to do that. And then I'm going to do a substitution, u equals sine x, and so I'm going to switch cosine squared x to 1 minus sine squared x, squared times sine x times cosine x dx. Everything here is correct here. And then I'm going to do a u equals sine x, du equals cosine x dx. And so what we get is an antiderivative 1 minus u squared times u times du. And you look at this, this isn't that bad to integrate. It's a polynomial. If you were clever here, I don't know if anyone did this, but with this antiderivative, you could do, again, let's just do this off to the side here. You could do a w is 1 minus u squared, and then dw would be negative 2u du. And if you did that substitution, what you'd get is w squared, and then the u du would give you, I guess, a negative 1/2 dw. So you'd get a negative 1/2 times w cubed over 3 plus c, and you could work on that way. So that would work out here. I don't know if anyone did that, and that's sort of fine. What I think people did here, something you can deal with, is you can square this here. So you get 1 minus 2u, 1 minus 2u squared plus u to the 4th. Then you multiply it by u du, and then you distribute the u. So you end up with u minus 2u cubed plus u to the 5th over 5 du. And then you integrate this, and you get u squared over 2 minus u to the 4th over 4 plus, sorry. I messed up the previous step, I'm noticing. 2u cubed, I don't get the over 5. I integrated this. It should have just been u to the 4th times u. So that's u to the 5th. Now let me integrate. Integrate u is u squared over 2 minus 2u to the 4th over 4 gives me a u to the 4th over 2. And then we get a plus u to the 6th over 6 here, plus c. And then you sub back in u with sine x here. And so you get a sine squared x over 2 minus sine to the 4th x over 2 plus sine to the 6th x over 6 plus c. Okay, and that everything there is just fine here, but it's more work than you really needed to do here. So let's go back to our original problem. Let's see if we can copy. Whoops, no, it's not going to let me copy that. Oh well. So what I'm going to get is cosine to the 5th x times sine x antiderivative. So I'm going to do an antiderivative cosine to the 5th x times sine x dx. So here's what I was hoping people would do. I think I saw a few of these. Is you say, well, I've got cosine to the 5th x, but I've got a sine x dx. And so what I want to do is use a u equals cosine x. Well, then du is negative sine x dx. And if you notice what happens here is I get an antiderivative, cosine to the 5th x, that's u to the 5th. Well, then you have sine x dx, that's pretty much du, I'm missing the negative. So you get a du and then a negative. And then you integrate this, and you get a negative u to the 6th over 6 plus c. So this is negative cosine to the 6th x over 6 plus c. So this is really the intent of the problem, not nearly as much work as the sort of other method. But either one's okay. I mean, they work out. It's just this one's much more efficient. Also note, I'm not going to show this here, but if you look at these answers look different. So presuming these are correct, you should be able to do some kind of trig identities to show that these two answers without the plus c's, they're either the same or maybe they differ by a constant here, which would be different c's here. So it sort of seems likely cosine to the 6th x, sine to the 6th x, should be about the same. But you get these other terms here as well. So you could play around with that and show those are the same. Next one. This one, we have an integral of x cubed over square root 1 minus x squared dx. Here there's a couple approaches here. I think I just want to show them both to give you some sense of what you can do. So the first thing I'm going to do is you'll notice the 1 minus x squared, and you might do a trig sub where you get x equals sine theta. And then dx is cosine theta d theta. So we do our substitution. X cubed is sine cubed theta over square root 1 minus sine squared theta. And then our dx becomes cosine theta d theta. Okay, so what you get then is, let's see, sine cubed theta over 1 minus sine squared theta is going to become a cosine squared theta square root. We're going to assume theta is between 0 and pi over 2, so that square root of the square is really just the positive version. Technically, it's an absolute value. And then we're going to get a cosine theta d theta. So this square root 1 minus sine squared theta essentially becomes cosine theta. And then our cosine thetas cancel, and you end up with an antiderivative of sine cubed theta d theta, which works out just fine. Here. Now, what you do with this is, I think, from the previous question, the kind of thing that people were doing with that cosine to the fifth. Here you do that here. So you take your sine cubed, and you split it up as a sine squared theta times a sine theta d theta. And then the sine squared theta, you write as 1 minus cosine squared theta times sine theta d theta. And now you can do a substitution where you're going to do u equals cosine theta. So u is cos theta, du is negative sine theta d theta. And so when you do that substitution, we get a 1 minus u squared. Sine theta d theta is basically du, but there's a negative that goes along with it. And so what you get then is negative, so when you anti-differentiate, you get a u minus u cubed over 3 plus c. So that's u cubed over 3 minus u if you distribute the negative. And so when you get done, you do, let's see, u is cos theta. So this is cos cubed theta over 3 minus cos theta plus c. But then we have to think x was sine theta. What's cos theta? Well, I can draw my right triangle here. I have theta, so x, where my x is sine theta. So sine theta, that's opposite over hypotenuse. I can make that x over 1 would give me x. Use the Pythagorean theorem here, and this other side will be square root 1 minus x squared. And so if you look at this, that means cos theta is square root 1 minus x squared. And what that means is I get, so you could write it as square root 1 minus x squared cubed over 3 minus square root 1 minus x squared plus c. So that's one way to do this, and I think I saw some people do this here. Fairly typical here. But there's another way to do this that's going to feel very different here. So we do x cubed over square root 1 minus x squared. Dx. And the other method is I'm just going to let u be 1 minus x squared. And so this one, you have to be a little more creative to make this work out, but it will. And then du is negative 2x dx. And so what I'm going to do is I'm going to take my x cubed, I'm going to write it as x squared over square root 1 minus x squared, and then the x, I'm missing an x from my x cubed, sort of times x dx. And when you do the substitution, you have this x squared. Well, if u is 1 minus x squared, you could solve that for x squared, get x squared is 1 minus u. So where the x squared is, you get a 1 minus u. Square root 1 minus x squared becomes square root u. And then your x dx, that's basically du, but you're missing a minus 2, so you get a negative 1/2 out in front. So a negative 1/2. And you get this antiderivative, which in this case is going to turn out you can actually do. And the trick here is you think of this as 1 over square root of u minus u over square root u. So you get a minus 1/2 times the antiderivative. 1 over square root u is u to the negative 1/2 minus u over square root u is square root u, or just square u to the 1/2. And then you do your antiderivatives. Here you're going to get u to the 1/2 over 1/2 minus u to the 3/2 over 3/2 plus c. And if you sort of dress this all up, let's see, we could distribute the negative 1/2. So you get negative 1/2 over 1/2. That's just a negative. U to the 1/2. U is 1 minus x squared to the 1/2, or minus square root 1 minus x squared. Note that's our second term up here. Minus minus becomes a plus, so we're working on our first term. You have your 3 in the bottom. The 2 and the 2 will cancel. So you get a 1/3, and then you get a square root, sorry, not square root, you get a 1 minus x squared to the 3/2 over 3. But that's the same thing as square root 1 minus x squared cubed. So square root's a 1/2. 1/2 times 3 is the 3/2. So there's a different way to do this. Very different feeling, but they both work. So it's sort of nice to have an idea of both of these. Okay, last one I want to talk about is a bonus question. I don't think anyone got this completely. I think we had a couple people I gave some points to here. One got really close with one little error here. But here's our bonus question. So this will take some work, but it's nice to see how these work out sometimes. So we're trying to do this antiderivative 8x squared plus 2x plus 7 over x minus 3 times x squared plus 2x plus 2. So the technique I'm going to use here is partial fractions. I have a factored denominator. Note, the top is degree 2. Bottom is degree, well, here's a 1 and a 2. 1 plus 2 is 3, so the bottom is degree 3. I don't have to do long division, which is nice. And so what I'm going to get is 8x squared plus 2x plus 7 over x minus 3 times x squared plus 2x plus 2. I want to write this as a over x minus 3 plus, if I have a denominator of x squared plus 2x plus 2, I'm going to write my numerator as bx plus c. So degree 2 on the bottom leads to degree 1 less than that, or degree 1 on top. I need to fill in everything. All right, now I'm going to multiply both sides by x minus 3 times x squared plus 2x plus 2. Gives me 8x squared plus 2x plus 7 equals, here the x minus 3's cancel. I'll get a times x squared plus 2x plus 2. Plus, on this one, the x squared plus 2x plus 2 will cancel. And I get a bx plus c times x minus 3. And you just need to solve for a, b, and c here. Now there's various methods to do this. One is to expand this thing on the right, equate coefficients of x squared of x in the constant term. You'll get 3 equations, 3 unknowns. You can solve that out. I tend to prefer to plug in values instead. So first thing I'm going to do is plug in x equals 3. Why 3? Because then this x minus 3 is 0, and this whole second term will just drop out. So I plug in a 3, let's see. 3 squared is 9, times 8 is 72, plus 6 is 78, plus 7 is 85. Let's see, 3 squared is 9, plus 2 times 3 is 6, 15, I get 17. So 85 is 17a, and then this term drops out. And so what you get is a is 85 over 17, which works out to just be 5 here. So 85 divided by 17 is 5. So we got a. Now there's nothing else I can plug in that will sort of zero out these other terms, so I'm going to try something simple. How about x equals 0? You do that on the left, you get 7. You'll get a 2a. Bx will be 0, and you get c times negative 3, so minus 3c. And we know a is 5, so 7 is 10 minus 3c gives us negative 3 equals negative 3c. We get c equals 1. So we get a and c. Let's go for b. Again, I don't have anything that's like going to zero things out, so I'm going to do an x equals 1 here. Sort of a simple number. So I do this on the left, I get 8. Plus 2 is 10, plus 7 is 17. You get 1 plus 2, that's 5 times a, minus, let's see, I get a b plus c here, and then I get a minus 2. So this gives me a, let's see, 17. A was 5, so 5 times 5 is 25, minus, let's see, I'm trying to find b. I know c is 1. b plus 1 times negative 2. How about we write that as a times 2 and change this negative to a plus here. I can move the 25 to the other side, and I get a negative 8 equals 2 times b plus 1. Divide by 2, and I get a negative 4 equals b plus 1. And then I subtract the 1 here, and I get a b is negative 5 here. So this should be what I get. Somehow I feel like I may have made a mistake there. I think that's not what I was supposed to get here. Yeah, something went wrong. So let's look at this again. I get 17 equals 5a. Let's see, minus 2. Oh, this minus here. I put a minus here thinking it was minus. That should have been a plus. So all this here is all not correct here. Generally correct, but I'm going to get rid of this and we'll solve this again. here. And so I get 17 equals 25. And now I'm going to get a, let's see, minus 2 times b plus 1. Subtract the 25 from both sides, you get a minus 8 equals negative 2 times b plus 1. Divide by the negative 2, which I had as a plus 2 before because I made an error with the sign. I get 4 equals b plus 1. Subtract the 1, and you get 3 equals b. Okay, so now I'm happier with that. Now what I get then is this whole integral I can write in this fashion here. So we're going to do that here. And so you're going to get an integral of a over x minus 3. A was 5. 5 over x minus 3. Plus bx plus c. That's 3x plus 1. Over x squared plus 2x plus 2 dx. Okay, so we get here. First integral, I can do that with a u equals x minus 3, and it's like a natural log of x minus 3. So when we do this, we're going to get a, we get a 5. Carries along 5 times natural log, really absolute value x minus 3. This one here, this second part, this is trickier. So what I'd really like to do is to let u be x squared plus 2x plus 2. So let's try that. And then du, I hope, is just the derivative of this, or some multiple of it, which I get 2x plus 2 dx here. But that's not the case here. I have a 3x plus 1. So what I'm going to do is I am going to rewrite this to make this sort of look right. So let's maybe rewrite our 2 times x plus 2, factor out the 2. 2 times x plus 1 dx. So I want this to be x squared plus 2x plus 2. If I had a 3x plus 3 there, I could do a 3 times x plus 1 would give me 3x plus 3, and I can work out the constants. So I can do that. But I can't just change that 1 to a 3, so I have to subtract 2 over x squared plus 2x plus 2 dx. Sorry, my writing on that side of the screen is not good. Okay, so now we have 2 integrals to do. So I'm going to keep the this integral. I can do my u substitution. So I'm going to get my 5 natural log absolute value x minus 3. And what I'm going to get here is plus. So I'm going to get an over u. I'd like to have a du. Let's do a 1 here. So this is a 3. Can pull a 3 out. And then I'm missing my factor of 2. So this should really be 3/2 here. Okay, so that's the first one. And then I can do a 1 over u antiderivative of natural log u, so things are good there. What do you do with this 2 over x squared plus 2x plus 1? Well, that one I'm going to rewrite in a different way. So I'm going to pull the 2 out. And I'm going to look at this bottom as x squared plus 2x plus 1 plus 1 here. Dx. Maybe seems a bit strange, but it's going to go somewhere. So we get 5 times natural log absolute value x minus 3 plus 3/2 natural log u, but u here was x squared plus 2x plus 2. And then this one I'm going to write as minus 2 times an antiderivative, 1 over x plus 1 squared plus 1. So essentially what I did is completed the square here on this first bit, and then I had a plus 1 left over. And now if you see 1 over u squared plus 1, where u is x plus 1, if you do that, du is dx. This, whoops, I have my dx. This integral is a 1 over u squared plus 1. Well, what's its antiderivative? That's an arctangent. And so what you get at the end of this all, let's maybe write that out here, is we get 5 times natural log absolute value x minus 3 plus 3/2 times natural log x squared plus 2x plus 2 minus 2 times an integral. This just becomes 1 over u squared plus 1 du. This antiderivative is an arctangent. So you get 5 times natural log x minus 3 plus 3/2 natural log x squared plus 2x plus 2 minus 2, and you get an inverse tangent or an arctangent of u plus c, and then u is just x plus 1. So when you're all done here, you get here all this stuff we've had. Whoops, not x. 2x plus 2. And then you get a minus 2 arctangent of x plus 1 plus c. So there's really our full antiderivative. So just sort of recapping what you needed to do here, what you need to recognize here. Whole thing. First thing, partial fractions you recognize. I think generally that's okay. You do that, and there's some work to be done. There's places to make mistakes there. But assuming you get that right, you get a fairly nice expansion. And then the maybe tricky thing is you have to realize, I have to split this 3x plus 1 up into 3x plus 3 and minus 2. And then you can do a u sub u is x squared plus 2x plus 2 on this first bit. And then to deal with this, you have to complete the square and turn that into an arctangent. So there's a fair amount going on here, but I guess that's why it's a bonus question.